Intermittent data loss, the invisible ghost in the hybrid machine, represents arguably the most expensive engineering nightmare of 2026. This isn't merely a minor inconvenience, it's a pervasive, often elusive problem that silently erodes data integrity and operational efficiency, leading to cascading failures and significant financial repercussions. We need to move decisively beyond the fallacy of reactive patching and the ingrained reboot culture that has plagued storage networks for far too long. This approach, while sometimes offering temporary respite, fundamentally fails to address the root causes of these complex issues, perpetuating a cycle of instability and unpredictability. Instead, we must confront the high-stakes intersection, where physical layer noise, often subtle and insidious, meets the intricate world of cloud virtualization, creating a perfect storm for data corruption and loss. This confluence of hardware vulnerabilities and software complexities is precisely where our focus must shift. We are not just talking about occasional dropped packets. We are addressing a systemic flaw in how our most critical data infrastructures are managed and understood. The challenge is immense, but the opportunity to redefine reliability is even greater. Our mission is to embark on a meticulous journey of hunting signals in the noise. This involves deploying cutting-edge methodologies and advanced instrumentation to detect the subtle precursors to data loss. A cornerstone of this approach is using real-time spectrum analysis to precisely identify electromagnetic interference (EMI) within high-density server racks. These racks, packed with an array of electronic components, are often breeding grounds for stray electromagnetic fields that can corrupt signals at a foundational level. By pinpointing these sources of interference with unprecedented accuracy, we can begin to understand their impact. Furthermore, we systematically map these physical layer errors against asynchronous buffer spikes, those sudden, transient overflows in data, cues that often indicate underlying network stress or corruption. This mapping process is crucial for uncovering hidden correlations and establishing definitive links between environmental factors and data integrity issues. It's about connecting the dots between seemingly disparate events. Through this rigorous analysis, we aim to isolate the specific environmental triggers, whether they are power fluctuations, crosstalk between cables, or even external radio frequency emissions, that cause those devastating, sub-millisecond packet drops. These microscopic events, though individually fleeting, collectively contribute to significant data loss, particularly in high-throughput, latency-sensitive environments. Following the identification of these subtle physical layer threats, our next critical step is decoding the gateway bottleneck. This phase delves deep into how virtualized storage gateways, which serve as crucial conduits for data flow between on-premises infrastructure and cloud environments, handle overflow conditions, especially during periods of peak asynchronous transfers. These gateways are often the unsung heroes of hybrid cloud, but they can also be the weakest link. We must analyze their behavior under stress to understand their true limitations. A particularly insidious phenomenon we investigate is the silent drop, where software logic within these gateways might inadvertently mask underlying hardware limitations. This can lead to packets being discarded without proper error reporting, creating a false sense of security and making troubleshooting incredibly difficult. The system appears operational, yet data is silently vanishing. To counteract this, we employ comprehensive stress testing methodologies designed specifically for the hybrid bridge. These tests are meticulously crafted to reveal precisely where logical buffers and error handling mechanisms fail when confronted with erratic physical signal quality. By intentionally pushing these systems to their breaking point, we can identify design deficiencies, configuration errors, or hardware weaknesses that lead to data loss under real-world, fluctuating conditions. This proactive analysis allows us to harden these critical components before they become sources of catastrophic failure. The culmination of these investigative phases is the forensic audit framework. This framework is a meticulously designed, non-destructive systematic audit of the entire hybrid data path, from the originating source in the data center to its eventual destination in the cloud, and back again. It's a holistic approach that leaves no stone unturned. Central to this framework is the utilization of advanced, automated telemetry tools. These tools are capable of collecting an immense volume of granular data from various points across the physical and virtual infrastructure. More importantly, they are synchronized to create a unified, high-resolution timeline of both physical and virtual events. This synchronized timeline is essential for precisely correlating occurrences, like an EMI spike with a subsequent buffer overflow and a reported data integrity error. We then verify data integrity at each and every hop along the data path. This isn't just about checksums at the endpoint. It's about validating data packets as they traverse switches, routers, virtual network functions, and cloud interconnects. By doing so, we can pinpoint the exact moment of packet expiration, identifying not just that data was lost, but precisely where and, most critically, why. Ultimately, our goal is engineering a resilient future. This involves a fundamental transition from the chaotic, often reactive troubleshooting that characterizes much of current IT operations to a standardized, repeatable recovery protocol. This new paradigm ensures that when incidents occur, they are handled with engineering precision, not guesswork. A key component of this future state is the deployment of predictive monitoring systems. These intelligent systems leverage the insights gained from our forensic audits to identify patterns and precursors of interference. They can then alert engineers to potential issues and signal degradation before data loss actually occurs, enabling proactive intervention rather than reactive damage control. This transforms the operational model from fix on fail to predict and prevent. By establishing these robust frameworks, we are not just solving a problem. We are setting a new professional gold standard for hybrid infrastructure maintenance and reliability. This standard will ensure that hybrid cloud environments are not just powerful and flexible, but also robustly dependable, guaranteeing data integrity and operational continuity. In the face of increasingly complex challenges, it's about moving from uncertainty to certainty, from chaos to control, in the crucial domain of data management.